Hello, my name is Benjamin Brandstetter, and today I'll be going over lab number 3, circuits. So what was the purpose of this lab? The purpose of this lab was to use real-world equipment such as resistors and batteries to test charge conservation, energy conservation through the loop rule, and to compare theoretical calculations to experimental results. The fundamental physical principles we used were Kirchhoff's loop rule, or the sum of the change in voltage around a circuit is zero, charge conservation, or the current in a steady state circuit is the same throughout series, Ohm's law, which is V equals IR, and for the RC circuit, delta V capacitor plus delta V resistor equals zero. The predicted results we had for the DC circuit were the theoretical total resistance was 147 ohms. The predicted current for the DC circuit was 3 over 147 amps. The assumptions and models we used were wires have negligible resistance, batteries are ideal and have constant voltage, the capacitor is ideal and has no leakage, and the voltmeter has ideal or infinite resistance. The models we used were ideal circuit component model, where our components are assumed to have ideal circumstances. Current is the same everywhere in the series at steady state. Kirchhoff's loop rule, and the time constant model, where the time constant equals resistance times capacitance. The experiment for the DC circuit, the system was the circuit that we were currently analyzing, and the surroundings were everything else in the universe. The initial conditions were the circuit is set up as instructed in the lab documents, and depending on what we were measuring, it was either left open or closed for a period of time. And the procedure was essentially just to use the real-world resistors and batteries that we were given to set up a circuit that was shown in a drawing on the lab documents. So the results for the DC circuit, I1 equals 0.02 amps and I2 equals that. When reversed, the ammeter had the same reading. Delta V across the 47 ohm resistor was negative 0.96 volts, and across the 100 ohm resistor, it was negative 2.04 volts, the negative signifying voltage drop. And then the sum should theoretically be zero due to the loop rule, and we found it to be zero, which means that those align. The potential verse position graph shows the voltage drop across different areas within the circuit. The slope of the graph represents the electrical field around that part of the circuit, the steeper being the greater the E field. So the conceptual questions, when you attach a voltmeter, why you're altering the circuit, why doesn't the ammeter reading change? The ammeter doesn't change because the voltmeters have extremely high resistance, which means they draw negligible current. When you replace the voltmeter with an ammeter in parallel with a 100 ohm resistor, what happens to the current through the other ammeter? When you replace the voltmeter with the ammeter, you're essentially short-circuiting the circuit, basically meaning that because we create a path of such low resistance, all or most of the charges are going to choose to take that path. This effectively lowers the total resistance of the circuit, causing the current to increase. So how close were the results? The results were aligned exactly with the theoretical calculations we had. The current was measured to be the same in two different places in the circuit, and the sum of the change in voltage was equal to the total voltage supplied by the battery, and the change across the resistors was equal to the current in the circuit multiplied by that resistance, which is just basically V equals IR. For the second part of the experiment, the RC circuit, the system and the surroundings were the same as the first part, where the circuit we are currently analyzing the system, and the surroundings is everything else in the universe. The initial conditions are also the same. We essentially just set up a circuit that was shown in the lab documents using real-world light bulbs and resistors. So the charging and discharging behavior observations, as time progressed after the circuit connected to the bulb started to dim. So essentially, the bulb started out very bright, and as the capacitor began to reach its maximum charge, it dimmed. This can also be explained by how the potential difference of a capacitor relates to time. As time goes on, the capacitor shifts from being a short circuit to its maximum voltage, where its current is at its lowest. That is shown in the formula to the right. And then once the battery is removed and the capacitor is discharging, the bulb initially was very bright and got more dim over time. So the charging and discharging times, essentially, we would assume that uh, theoretically it should take more time for the capacitor to charge with a light bulb that has a higher resistance than one with a lower resistance, and that's exactly what we found. The times were lower for the lower resistance bulb. Possible source of error. The circuit elements could have been non-ideal, meaning the wire could have some amount of resistance. The temperature or humidity in the room could have affected the flow of charge, and then some human error with the timing could have affected our times. The what if question, what if you charge a capacitor in a circuit with no resistor? How quickly would the ideal model predict it to charge? Theoretically, the charge would be instant. However, when done experimentally, the capacitor did not change instantly, but took a small amount of time to charge, which reveals the non-ideal nature of real-world circuits. So this lab showed that current is conserved in a series circuit. that the loop rule is true, that sum of the potential difference across all circuit elements is 0, and it showed that the time constant is consistent with the experimental results of charge and discharge. Thank you.